Welcome to the video lecture series on Taylor and Laurent series in complex analysis. I'm Mayur Gohil. In this video lecture, let us see a new kind of a question where we are said for the following function f of z equals to z upon z minus 1 into 2 minus z. We are asked to find the Laurent series expansion for and we are also asked to find the region of convergence, indicating the region, and we have to draw. So there are three things we have to do. First, we have to find the region of convergence. We have to find the Laurent series expansion, and we have to draw the region of convergence. That is not a big task, but let us see how to go about this kind of a question where we are not given the region of convergence and we have to find it from the question. So let us see how to do about this kind of a question. So first thing here we see our step number one in solving the question will be we first go for the partial fraction. Okay, so solve for the fraction of f of z. Okay, once you solve for the partial fraction you will be getting almost all your answers easily, but don't make mistake over here. So we have our function, we have f of z equal to z upon z minus 1 times 2 minus z. Then consider z upon z minus 1 into 2 minus z equal to a upon z minus 1 plus b upon 2 minus z. Now z equal to a times 2 minus z plus b times z minus 1. I'll call this equation with some new label. I'll call this as here we'll call it as this, we call it as 1, this we call as 2, this one we'll call as 3. Okay, now once we label this, now we go for solving. Put z equal to 1. The moment I put z equals to 1, so 1 is equals to a times 2 minus 1 plus b times 1 minus 1 that we will get here. Therefore 1 is equals to a. Now put z equals to 2. Moment I put z equals to 2, I get 2 is equals to a times 2 minus 2. Yeah, all these we are putting in the equation 3. Okay, if you are not aware, then I'm putting everything in equation 3. Putting z equals to 2 in 3, you get 2 equals to a 2 minus 2 plus b 2 minus 1. Okay, now what do we get over here is 2 is equals to b. Therefore our required partial fraction, therefore f of z can be written now. See, the from 2 we will get everything. Okay, from 1 and 2 if you see, f of z is nothing but the LHS. So f of z equals to a upon, so a has come down to be 1, so it is going to be z minus 1, and b has come down to be 2, 2 upon 2 minus z. Now comes the whole part. See, we have to find the region of convergence. So region of convergence we will get over here from the partial fraction, or we could have also got it from equation 1, but let me take you through the partial fraction. From the partial fraction over here which we got, let me call this as equation number 4. I'll put it a blue mark with over here. So this partial fraction, note how to find the region of convergence. So here I'll write this. Okay. For finding region of convergence, see where the denominator becomes 0 in equation 4. Okay, so in equation 4, that is the place in equation 4. Okay, now, so when you see that, you come to know that z equal to 1 and z equal to 2 are the points, are the points, rather they are called singularity. In this topic I have not discussed about singularity, so but rather we can right now keep it in that simple manner. So are the points at which denominator is 0. So now we see that 1 and 2 are different points, right? Z equal to 1 is 1 here you have, and here 2, they both are distinct. Now because they are distinct meaning they are different, so we now get three regions over here. Okay, see the way they are written. Now remember here carefully that when you get 2 points like this, if one point is negative, other point is positive, take the modulus of each of them. Okay, take the modulus of each of them. So take always the absolute value, I would like to say that. So here z is equals to 1 and z equals to 2. So obviously we can now understand that 1 is less than 2. So what will happen now? So we write down the region of convergence now. So here, therefore, the region of convergence R, the first region will become mod of z. Okay, mod of z. If no center is mentioned, you always take the center as origin. Nothing is mentioned, so we will take the center as origin. So mod of z is less than, which is the smallest number of 1 and 2, take that, is less than 1. That is the first thing. Second is, it will lie between the first number, the mod of z will lie between the first number, the smallest of the two, 1, and the largest. Okay, so it will lie between 1 and 2. Number 3 will be the mod of z is greater than 2. Okay, so I mean to say 2 is going to be less than mod of z. So these are the three important region of convergence that you will get when you solve this question. Okay, anytime when you have two numbers which are different, then you get these three regions. Okay, now uh, there is one important thing you have to remember. If there is, suppose you have over here z equal to 0 and then there is 2, then in that case you will get only two regions. Okay, because if suppose a number is 0 I'll just write here with the purple color. If z equals to 0 and you have z equal to 2, okay, suppose. Instead, then what regions you would get? Then you have only this region, okay. uh, 0 is less than mod z less than 2. This is one region. Another region you will have 2 is less than mod z. Okay, you can't have this region that mod z being less than 0. It is impossible. It mathematically it is not correct. Then there is no sense also making such kind of region that is mod z less than 0. It is senseless. Okay, remember this, because mod z itself is radius. Radius cannot go negative. That is the fixed notion in mathematics. So radius is never negative, so we cannot say mod z is less than 0. Okay, so remember, if there is one of the value is 0, then you will have only two regions. But if both the values are non-zero, then you will have three regions of convergence. Okay, so regions of convergence are these. Okay, three regions are there. Now let us see how to solve over here. So I'll just put a nice separator to understand that we are going column by column. Okay. Now let us see what happens in case number 1, how to solve for case number 1, the Laurent series expansion. So for case 1, case 1 says that mod z is less than 1. So there is a meaning here. When mod z is less than 1, it is also less than 2, which implies that mod z is less than 2. Now when mod z is less than 2, this, and remember, now we have to make everything less than 1. So when we have to make everything less than 1, so mod z upon 2 is less than 1 now. Therefore, now these terms that we have got without mod, we have to establish in the partial fraction expression 4. Okay, the fourth expression. So let us see what happens there. So therefore, f of z equal to 1 upon z minus 1 plus 2 upon 2 minus z. Now we have to bring these terms. So firstly I'll write here minus 1 upon 1 minus z. I have taken minus sign common from the denominator and I'm writing it above. In the second expression, what do we have to do? We will take 2 common. What happens is 2 upon 2 and 1 minus z upon 2. This is what we get. This 2 and 2 gets cancelled. So now what we are left over here is minus of 1 upon 1 minus z plus 1 upon 1 minus z upon 2. Now we go for writing the expansion of the series. So expansion of the series, when we have to write over here, what will happen? This is, we write the expansion over here. So it is of the form 1 upon 1 minus z. So the expansion that we had given in the video lecture number 1 on Taylor and Laurent series, it will be, so this minus sign remains outside and there is summation z to the power k, k going from 0 to infinity, summation z upon 2 whole to the power k, k going from 0 to infinity. This is the answer. Now we can take terms common because this minus sign is there and runner k is going from 0 to infinity, and z to the power k, z to the power k, both the places they are in the numerator and all are going to have positive power, so simplification is possible over here. So I'll write, so summation, here we will have minus 1, because this minus sign will go inside, right? And from here you will have in the second part, what is the coefficient of z to the power k? It is 1 upon 2 whole raised to k. This is the coefficient, okay? And this is z raised to k. So, and this k is going from 0 to infinity. So this is the output for the case number 1. So this is your final answer, okay? So that yeah, so this 26 you can just ignore for some time, that's the slide number. So here you have the final answer of the for the case 1. Okay, now let us see what will happen for case number 2 and 3. So this is the Laurent series expansion in case number 1. Now let us go for case number 2. So we remembered this partial fraction clearly, that it is 1 upon z minus 1 plus 2 upon 2 minus z, okay? So because we will need it all throughout. Now let us go for case number 2. Case number 2. 1 is less than mod z less than 2. So this means that 1 is less than mod z and mod z is less than 2. So our goal in the mind should be that we have to make everything less than 1. So making everything less than 1 meaning 1 upon mod z is less than 1 and mod z upon 2 is less than 1. Now these terms without the mod 1 upon z and z upon 2 we have to establish inside the partial fraction equation 4 that we had seen. So partial fraction that we had seen was f of z is, it was 1 upon z minus 1. Here it has 2 upon 2 minus z, okay? This is from 4, from equation number 4 we got. Now let us see how to simplify this according to case number 2. So what do we need is 1 upon mod z is required and z upon 2 is required in the partial fraction. So let us settle down that term properly. So this will happen here. What will happen is we take z common. The moment I take z common, it becomes 1 upon 1 minus z. And in the second part, there is no change at all, because this 2, who when you take common, it is just as the same previous part. It will become 1 upon 1 minus z upon 2, just like the case number 1. Okay, now what we do, we see that we have an expansion 1 upon z. The first term remains as it is, but 1 upon 1 minus z, 1 upon 1 minus 1 upon z, this term has its own expansion, right? This term can be written in the expansion format. So the summation here, it will be 1 upon z whole to the power k, k going from 0 to infinity. Now here you will have the same expansion as we had for in case number 1. So it will be summation z upon 2 whole to the power k, k going from 0 to infinity. So summation 1 upon z whole raised to k plus 1, k going from 0 to infinity, plus summation z upon 2 whole raised to k going from 0 to infinity. Now this, there is no chance of expanding or simplifying, means you can expand these summations, the infinite series they are, you can expand, there is no problem, but this is the same answer it's going to remain. Okay, so this is the Laurent series expansion for case number 2. You can stop your answer over here for case number 2. Now let us go for case number 3. 2 is less than mod z. Now, what is the meaning over here? It means that 1 is less than 2 and 2 is less than mod z. So this means that 1 is also less than mod z. So now we have two meanings here, and this is very obvious that 2 is less than mod z. So this means that 1 upon mod z is less than 1 and 2 upon mod z is less than 1. Okay. Now this terms we have to establish inside the partial fraction without the mod sign. So let us see how to establish it inside the partial fraction. So f of z partial fraction we have written down here. So 1 upon z minus 1 plus 2 upon 2 minus z. Now we simplify this carefully. So 1 upon z, you take common, you have 1 upon 1 minus 1 upon z plus 2 times, now we need 2 upon z, so again take z common over here, so you get 2 upon z minus 1. Now see, you have got 2 upon z, right? So 2 upon z minus 1, we don't have the expansion format in this way, we have 1 minus, right? 1 upon 1 minus is the format for our expansion. We have seen in the all the video lectures previously that we have expansion in this 1 upon 1 minus z or 1 upon 1 plus z is the format. So what we do, we will take minus sign also common, so here it is 1 upon z and plus we take minus sign common, then it will become minus of 2 upon z times 1 minus 2 by z. Okay, this is what we will get. So this will now get us what we want. So 1 upon z as it is, and here the expansion will work, and this will be summation 1 upon z whole raised to k going from 0 to infinity. Here it will be minus 2 upon z summation 2 upon z whole raised to k going from 0 to infinity. This is what we will get. Now let us simplify this further, because the terms are it is possible to take terms common and write a bit more about them. So let us see how to go about that. So f of z can be now, you take this 1 upon z over here which is there, you take it inside. So the power of k which you see there, it will increase. So you have over here 1 upon z to the power k plus 1, and k will start from 0 to and end on infinity. Okay, that will remain same. Now you can see that this 2 upon z is there, that also can be pushed inside the summation, so it will become minus here, and then there is summation 2 upon z whole raised to k plus 1, k going from 0 to infinity. Now this can be your final answer, it's not an issue, but simplification is possible, so please simplify this a bit. So what you will get is here summation you take common. So when you take summation common, you get k going from 0 to infinity, and in the first part you will get 1. Okay, see, 1 upon z to the power k plus 1 is there, and here in the second part the coefficient of 1 upon z to the power k plus 1 is 2 to the power k plus 1, and with there is a minus sign over here. Okay, so there is minus 2 to the power k plus 1, and here outside you will have this z to the power k plus 1. This is what the expansion of Laurent series for case 3. Now we are asked to draw the diagrams for each of the case. So let us see how to draw the diagram. It's very easy and very simple, okay? But each time only one thing you have to remember. For case 1, I'll just draw the diagram all three over here. So for case 1, the diagrams, okay? Now I'll just put a label over here, diagrams of regions of convergence. Convergence. Now remember that when you are drawing diagram for each of the region, so the region I'll write here, the first region we had for 1, when mod z is less than 1. So what we need is we need a circle centered at origin. Okay, we are taking center at origin and the radius of the circle is 1. And remember, because this circle boundary is not included, so you will be expected to draw a dotted circle. Okay, a dotted circle is expected to be drawn, and the center, and this center, please put a hollow dot over here. Okay, the center is basically not included in the circle over here. This is very important. And we have to shade the region. It is the interior of this circle without the center. So I'm now shading the circle region. So it is this. It is the whole interior that we have to take, but the boundary is not included and the center is not included. So this is the kind of the circle you will have. Now for case number 2. For case 2, I'll draw over here. For case 2, we had here it was 1 is less than mod z less than 2. Now let us see what happens here. In this case we will have a circle centered at origin. Okay, centered at origin. Now there are two circles, concentric circles we have to draw. Okay, so I'll draw one circle here. Again remember, it will be a dotted circle. Okay, I think I'll take the center over here. Just a minute. You can draw freehand. There is no need to use the geometric tools. Freehand understanding of the circle. If once you get the understanding, that's this is a circle over here, and then the radius of this circle is going to be 1. Okay, and here you have another circle of radius 2. So that circle is also dotted like this. Okay, and the region, yeah, so that circle will be having radius 2. There is a radius 2, and again over here remember the circle center is not included, so better put a hollow, uh, I'll just put with a yellow, put a hollow circle over here, make it hollow. Okay, it should not be dark. Okay, keep it hollow. Now, yeah, what about the region? The region of convergence I'm shading now. The region is going to be this green one that I'm shading. It is the annular region. Okay, it is this annular region there that is expected. So this is the second, for second case. Now for the third case, I'll put the separator first. So this is for case number 2, and now for case number 3 we have 2 is less than mod z, right? Remember the circle should be a dotted circle. Okay, this is the dotted circle, and it is centered at origin. So here we put a hollow center. Okay, keep it hollow, and put your sign of radius and 2. And for shading of the region we will have to shade the exterior, so I'm shading with this green color over here. So it is the exterior that is to be shaded. Okay, so this is the region that is to be shaded when the uh, mod z is greater than 2. Okay, so these are the three regions of convergence that I have shown over here. Remember, in each of the three cases we have to draw dotted circle, not the circle in a regular way that we draw. We just have to put a dotted circle, so put dash dash over there while making the circumference of the circle. Okay, so I hope you have followed this example that I have taken. Now, this is a very common kind of question which is asked generally in the exam, in most of the examination, where the students are given a function and all the three regions are asked by the questionnaire to the students to find on their own. So this is how you find the region over here, and you are also expected to draw sometimes. So these are the three regions that I have given over here. Please go through the entire question once again. If you haven't followed anything, please feel free to comment in the comment section. I would be really happy to help you and solve your doubt. I request you to hit like button, share it with your friends, those who have this topic and will benefit from it. Subscribe to my channel. Thanks for watching the video. I'll join you in the next video lecture. See you soon. Till then, keep solving good amount of mathematics.